Hi. We've now discussed the historical origins of commutative algebra, how it arose from number theory and invariant theory and algebraic geometry, and now we'll move on to define rigorously the star players in commutative algebra, which is the ring. So we'll start by defining a ring. Okay. So we're going to let A be a set with two binary operations we'll call them addition and multiplication, such that, so first of all, A plus, so the set A endowed with the addition operation is an abelian group. Okay. And the group operations, the group axioms you would expect it to satisfy include the fact that we have a zero element, which is the additive identity. It has additive inverses, so plug that in there. And the addition is commutative, so plus is comm. Okay, so that's the first thing we're going to require for a ring. Second, the multiplication, while it doesn't form a group with A, we do have that the multiplication is associative. And it distributes over the addition on the left and the right. Okay, so what that means concretely is if we have A, B, C, so the associativity means that A times BC is the same as AB times C. And as for the distributivity, we have A times B plus C is equal to AB plus AC, so this is distributing from the left, and then A plus B times C distributes on the right, so we get AC plus BC. Okay, so that's the distributive properties. And then we have that because we're working with commutative algebra, our rings are all going to be commutative unless indicated otherwise. So multiplication is commutative for a commutative ring. And that means concretely that xy will be equal to yx, and we have an identity, a multiplicative identity element. So we have 1a, which is a multiplicative identity. So there are some older sources where you don't require a multiplicative identity for a ring, but in more modern sources, everybody requires a multiplicative identity. So now I want to ask, is the abelian group axiom necessary? So let's say we had everything else in this definition of a ring, but we didn't have that the addition was commutative. So could we derive that from the other axioms of the ring? And the answer is yes. And let's look at how we would do that. So we're going to use the fact that we have a unit, a multiplicative identity. So let's note that we use 1a as multiplicative identity. In that case, we're going to consider 1a plus x times 1a plus y. Okay? So now we're going to use the distributive properties to carry out this multiplication. But we want to keep in mind that we have a left distributive property and a right distributive property. So if we want to distribute this on the left, we're going to get 1a plus x times 1a plus 1a plus x times y. Okay, and distributing again, this time on the right, we have 1a times 1a is just 1a because it's a multiplicative identity. Similarly, we get x, we get 1a times y is y, and we get x times y is xy. Okay? And we're not assuming that multiplication is commutative in this derivation. So let's say instead of distributing on the left first and then the right, let's do the other way around. So now we have 1a times 1a plus y plus x times 1a plus y. This is going to be equal to 1a times 1a is 1a plus y plus x plus xy. Okay, so now this time we distributed first on the right, then on the left. And what we see after we do cancellation, which is obviously allowed since we have a group under addition, so we can cancel this on the left, cancel this on the right, and what we've learned from the distributive properties is that x plus y equals y plus x. So technically we could drop that from our set of axioms altogether. What if we drop other properties? So let's say instead of requiring an abelian group under addition, let's say we just needed a semigroup so that we did not require additive inverses. Okay? So we're looking at a semigroup instead of a group under addition. Okay, well in that case, what we get is called a semi-ring. And an example of this is the tropical semi-ring. And this is a very cool object to study. It has enormous applications in algebraic geometry, and it would make a great research project topic. So definitely look into that. Let's say instead of leaving out additive inverses, we don't require the multiplicative identity. As we said before, this was not always required by earlier sources, but these days if you have no multiplicative identity, what's left is called a rung. The idea being that it's missing the I, which would be your multiplicative identity. And these are, for these, you could basically think of this as any two-sided ideal in a ring. What if you allow, what if you say that the ring has to be, the multiplication has to distribute only on one side and not on the other side, and that the underlying group, that the group with addition is not abelian, right? So when we did this proof up here, we used the fact that we distribute on the left and the right to prove that the group under addition is abelian. But if we're only distributing on one side, the group isn't necessarily abelian. Well, what you get when you do that is called a near ring. And an example of that is functions on a group. And this is another interesting topic which you might want to research. Okay, so you can see that when we drop any property, we get something that has its own rich structure, but it's the ingredients to a ring that gives us this object that has become the focus of so much study over the past centuries. Okay, so let's talk some examples. What are some rings, some commutative rings that you probably know already? Well, we have the integers, standard addition and multiplication. We have the rationals, the real numbers, complex numbers, we also have the ring of integers modulo some fixed n. So for example, if you had n equals 2, then you would get the ring with two elements, 0 and 1. Okay. Another example would be R adjoin X. This is the ring of polynomials in X with coefficients in R. Let's get a little demarcation in here. And we also have, with two brackets, this indicates the ring of power series in X with coefficients in R. And R can be any ring. And one other one that you might not have considered in the past is the set of continuous functions on some topological space X. Space X. So this is also a ring under pointwise addition and multiplication. Okay, but even though we're studying commutative algebra, it's still helpful to remind ourselves what some non-commutative rings look like. So one classic non-commutative ring is the ring of quaternions. The Hamilton quaternions. And this is the set of numbers of the form a plus bi plus cj plus dk satisfying I squared equals j squared equals k squared equals minus 1 and ijk equals 1 or minus 1. No, let's hedge in case I got the sign wrong. Another non-commutative ring is the set of n by n matrices with entries in R, where R is some ring. Okay, so these are well known not to commute. Okay, and another non-commutative ring is a group ring over a non-abelian group. And this is basically formal sums where you write aigi over some index set, and ai is in your ring R, and gi is in your group. And then addition, you just add it to the formal sum. As for multiplication, you take ai, or rather, let's make it ag times bh. That's going to be equal to ab times gh, where this is multiplication in the ring, and this is the group operation. And you can extend out, based on this rule, you can extend out to formal sums just using distributivity. Okay, so now we've gotten to see some rings, and now we can talk about what a ring homomorphism is. So a ring homomorphism is a map F from a ring A to a ring B, satisfying, basically respecting the structure of the ring. So we want to make sure it satisfies, first of all, that it makes sense with addition. So f of x plus y is equal to f of x plus f of y. It also commutes with multiplication. F of xy equals f of x times f of y. And it respects the identity. So f of the identity element in A is going to be the identity element of B. Okay. And if you wanted some examples of ring homomorphisms, you could say, for instance, mapping Z to Q and just sending every integer to itself is a perfectly good ring homomorphism. Sending Z to Z mod n by sending every element to its equivalence class mod n, that's also a good homomorphism. And another one, I'll just say n maps to n. And another homomorphism would be if we have polynomials with coefficients in the rationals, and we map to the rationals by saying, let's consider these as functions of x, take p of x, and evaluate it at x equals 1. Okay, these are all homomorphisms. Okay, but I want to pause and think a little bit more about how homomorphisms act on our identities. So one of our rules was that f of 1 has to equal 1, right? So we were told f of 1 equals f of 1a equals 1b. But what about f of 0? Okay, so the reason we don't need to write explicitly that f of 0 equals 0 is because it follows immediately from the other rules of the homomorphisms. We saw that f of a plus b must be equal to f of a plus f of b, but then that means that f of a plus 0a has to be equal to f of a plus f of 0a. But if I do the addition first, that's just equal to f of a. Right? Let's move this over a tad. So that tells us that because we have this is equal to this, we can cancel the f of a's to obtain f of 0a equals the 0 element in B. Okay, let's move forward. To define a subring, it's pretty straightforward. If you have S contained in your ring A, and the identity element is in there, and S is closed under addition and multiplication, then we say that S is a subring of A. Okay? And some examples of subrings. So we've seen already that Z is a subring of the rationals. So the integers is a subring of the rationals, right? 1 is both an integer and a rational number. Okay. Another ring which has Z as a subring is the ring of polynomials with integer coefficients. Right? Because if you take the constant polynomials in that ring, that's just the integers. And if you want to take a ring which has both of these as subrings, that would be the ring of polynomials with rational coefficients. Okay? And you can convince yourself that all of these subring relationships hold. Okay, now let's talk about ideals and quotients. So I'm going to try to attempt writing a mathfrak script. So let's give it a fracture script. So an ideal of A is an additive subgroup. Okay, now here's my attempt at fracture. Okay, oh, yikes. That's bad news. Let me try one more time. Okay, that'll be my A. It's an additive subgroup A and A, closed under multiplication by A. So in particular, if you take any element, so for any x in A, and A in fancy A, ideal A, then we have XA is also in the ideal A. I think I'm getting better at this fracture script as I go. As for a quotient, so if you have an ideal A, the quotient, so the quotient A mod A is given by this. It's the set R plus A. This is a set of equivalence classes mod A. Okay, this is the set where R is any element of A. And addition is just given by R plus A plus S plus A is just R plus S plus A. So that's how you do addition in the quotient. In terms of multiplication, R plus A times S plus A will be given by RS plus A. Okay. So a natural question to ask is, why must the ideals be closed under multiplication by A? Right? Why isn't enough that an ideal should be an additive subgroup. And that'll be an important object to study with rings. And the reason is basically so that we can define the quotient and it will be well defined. So in order to have r plus a times s plus a to be equal to rs plus a, then this also has to make sense if I take different representatives of each of these equivalence classes. So for instance, if I take r plus a times s plus b, where a and b are in the ideal, so I should be able to demonstrate that what I get is in the same equivalence class modulo of the ideal as rs. So using distributivity, we get rs plus as plus rb plus ab. Okay? And so we want this to be equivalent to rs mod a. Well, in order for this to be true, we need as plus rb plus ab to be in the ideal. Okay? And to simplify this, we could say, let's set r equal to 0, and since r, or rather not r, let's set a equal to 0. Okay, because this is supposed to work for any element of the ideal, and 0 is in every ideal. Then what we're saying is rb must be in A. Okay? Which means that for any element in the ring R, because R is any element in the ring and B is any element in the ideal, this means that you must have closure under multiplication by A. Okay? Hopefully that's clear. Okay, now looking a bit closer at quotients, we have a proposition from Mattia MacDonald, 1.1, that there's a one-to-one order-preserving correspondence between ideals B in A, containing A, and ideals B tilde in the quotient ring A mod A. Okay, so I won't give a proof of this, but I will give an illustration. So if we want to think about the ring A equals Z, and the ideal A equals 20Z, okay, just multiples of 20, then let's think of all of the ideals that contain A. So ideals containing A. So when we think of sets that contain the multiples of 20, it's going to be determined by factors of 20. So we have the whole ring, we have even numbers, multiples of 4, multiples of 5, and multiples of 10. Okay. As for ideals in the quotient ring, so in Z mod 20Z, the ideals are the whole ring, just the even numbers in the ring, so 0, 2, 4, up to 18, 4Z mod 20Z, 5Z mod 20Z, and 10Z mod 20Z. So that's just 0 and 10. So as you can see, these are in clear bijection, the ideals containing A and the ideals of the quotient ring. Okay. Now let's look at homomorphisms once again. So we're talking about kernel and image. So first we want to observe that the kernel, so if we have, so let f be a ring homomorphism. We're going to define the kernel of F to be, and let's actually make this, let's give explicit rings here. This is going to be a ring homomorphism. The kernel of F is equal to the set of x in A such that f of x equals 0. And the image of F is equal to the set of x in B such that there exists y in A with f of y equals x. Okay, and these are your standard definitions for kernel and image. But what we do want to point out is that the kernel is an ideal. Okay. And how could we demonstrate that? Well, if f of x equals 0, then that means that f of ax equals f of a f of x, but this is 0, so this is just equal to 0. So that means that ax is also in the kernel, which means it's closed under multiplication by elements of A. Okay, so that's how this is an ideal. The image is also a subring. A subring, so we just need to show that it's closed under multiplication and addition, and you can do that using the properties of homomorphisms. As for demonstrating that 1 is in the image, well, we have the rule that, so f of 1a equals 1b, so 1b is certainly in the image. And closure under multiplication and addition, you have f of x plus f of y will be equal to f of x plus y. And the same is true for multiplication. I'll just give 3 dots to remind you of that. Okay, now let's define a zero divisor. So a zero divisor is, so we have a ring A is a ring, then x in A is a zero divisor. And sometimes people write this without the hyphen, but I usually write it with the hyphen. It's a zero divisor if there exists a y in A such that xy equals 0. Okay? And just to say a few examples of this, so in the ring z mod 6z, 2 and 3 are zero divisors, because when you multiply them by each other, this should be, there's a y and an a with y not equal to 0, such that xy equals 0. Let me make this a little neater. Y not equal to 0. Okay, and so neither 2 or 3 are equal to 0, and yet 2 times 3 equals 0. Okay, another example, if we want to think about continuous functions on the unit interval, then if you think about the function that looks like this, where you start with identically 0, and then you have a line going up to 1. So this is a function. This is the graph of a function from the interval to the real numbers. And this is a zero divisor, because if I were to multiply it by a corresponding function where you have the support entirely complementary to the support of the other function, then when you multiply them together pointwise, you'll get 0. So these are both zero divisors. Okay. And one more point to make before we move on. is that a ring without zero divisors is an integral domain. That's the name for it. Okay. Now let's define a nilpotent element. So again, we're working in a ring A. So let A be a ring. X in A is nilpotent if there exists a positive integer n such that x to the n equals 0. Okay, and let's say a couple of examples of that. So if you have the ring Z mod 8Z, then the element 2 is a nilpotent element, because when you raise it to the third power, you get 8, which is in the equivalence class of 0 in this ring. So 2 is nilpotent. Another example, which is not in a commutative ring, is the 2 by 2 matrix 0, 0, 0, 1, 0, 0. So when you square this matrix, because it's essentially mapping the second basis vector to the first basis vector, and the first basis vector to 0. So if you do that twice, everything gets mapped to 0. So this is also a nilpotent element, though we should note this is not a commutative ring. Okay, and this is in M2 of R, let's say. Okay, so we know what ideals are. A principal ideal is an ideal which you can describe as the multiples, all multiples of some element x in your ring. Okay, and sometimes you'll write this as, so you can write this written as parentheses x or ax, okay, indicating that you're multiplying all elements of A by x. So let's do a couple examples of principal ideals. 12z is the multiples of 12 in the integers. That's a principal ideal because it's generated by 12. Is a principal ideal. And we can keep in mind this includes 12, 24, minus 12, etc. Another principal ideal is all multiples of x squared minus 1 in the ring of polynomials with rational coefficients. Okay, and here it's all polynomial multiples, so here you'll have x squared minus 1, but you'll also have x cubed minus x. You'll have 2x squared minus 2. And then you also have things that you get from adding these together. So for instance, x cubed plus x squared minus x minus 1. Okay. And obviously that does not exhaust the list of multiples. Okay, if you want to know something that's not principal, then you could take the ideal, the smallest ideal containing 2 and x in the ring of polynomials with integer coefficients. So you can convince yourself that this is not the whole ring, and yet there's no single element which has both x and 2 as a multiple. So you need both of these in order to generate the ideal. Okay. Thank you for staying with me through this. It's a lot of definitions, but we need this in order to move forward in the course. Okay, so if we take A a ring, then X in A is a unit if there exists a Y in A such that XY equals the identity, the multiplicative identity. If all elements of A are units, then A is a field. That's the name. Okay. And we'll conclude this lecture with proposition 1.2 in Atiyah McDonald. If you have a non-zero ring A, then the following are equivalent. First, A is a field. Second, the only ideals of A are 0 and 1, where 1 generates the whole ring. And third, every homomorphism of A to a non-zero ring B is injective. Okay? So in terms of how these are all related, so for 1 and 2, if everything is a unit, then then for any element you take X, if you want to look at the principal ideal associated to it. So this will include XY equals 1 for some Y, right? Because everything is a unit. But that means that it's the whole ring, unless X is 0. Equals 1 implies that it's the whole ring, unless X equals 0. In terms of how 3 is connected, so so if you wanted to know how 2 implies 3, well, consider the kernel of homomorphisms from A to B. So the kernel of F from A to B, we know that kernels are ideals. So either the kernel is the whole ring, which means it maps everything to 0, which is not possible since B is non-zero, and that would otherwise violate the requirement that 1 maps to 1. Okay, so kernel of F is not the whole ring, but then that means that it has to be the 0 ideal, because that's the only other ideal that we have. So this means that kernel of F must be equal to 0, and when you have the kernel being equal to 0, that means that F is injective. Okay, so I look forward to going over this material with you in our group work sessions, and have a great day.